If you want to take a seat, maybe we can start with the second plenary session of the day. Okay, so welcome everybody to our second plenary session for our second day of this amazing conference organized by the International Institute of Forecaster. My name is Malvina. I have just joined the IIF board, and I have the great pleasure and honor to introduce you all to our keynote speaker, Professor Dolores Romero Morales. Professor Morales is a professor of operations research at Copenhagen Business School, and her areas of expertise include data science, supply chain optimization, and revenue management. In data science, she investigates explainability, interpretability, visualization matters, and fairness. And I think a large share of the talk of today is going to be about this very interesting concept of fairness. In supply chain optimization, she works on environmental issues and robustness. And in revenue management, she works on large-scale network models. Her work has appeared in a large number of top journals, including EJOR, the European Journal of Operational Research, Management Science, Mathematical Programming, and Operational Research. And she has received a large number of distinctions. Currently, she is the editor-in-chief of TOP, which is the Operational Research Journal of the Spanish Society of Statistics. And she's an associate editor of the Journal of the Operational Research Society Omega and the Informs Journal on Data Science. Now, in addition to her amazing academic achievements, Professor Morales has also worked for a long time advising various companies on these topics, including IBM, SAS, KLM, and Radisson Edward Hotels. And the result of her collaboration with this institution, she has managed to help them improve many of their practices. SAS named her an honorary essays fellow and a member of the SAS academic advisory boards. Okay. I could continue for the whole afternoon just telling you how great she is, but I think I need to leave you to enjoy this paper she's going to discuss with us today on the mathematical modeling and optimization for explainable and fair machine learning. So let us all welcome Professor Morales.
So thank you very much for the kind invitation, and thank you everybody for rushing after your lunch to listen to my talk. So my talk is going to be about explainable and fair machine learning, and what I'm going to do is give you a little bit of a tour of what I do with many PhD students back in Copenhagen, where I'm based, and also my hometown, which is Seville. So it's going to be flashes of different papers, but I hope I get the message that with operations research, which is my expertise, we can achieve a much better level of fairness without harming accuracy. So that's going to be the summary of my talk. So if you want to go away and come back in 45 minutes for the questions, do that. Okay, so I'm going to show you a few references in this slide that talks about transparency. Now, this is a word that is being used a lot at the moment. So we think that machine learning models are black boxes, and I have heard this also in this conference. And we are trying to make those black boxes a little bit more gray than black, and we do that in different ways. So the first thing to say is this transparency that we are talking right now is not a new thing. So we have had many names for a long time trying to talk about these methodologies that are a little bit easier to understand. So interpretability, comprehensibility, those are words that have been in the literature for a long time. And I have there a reference from Management Science from 2003, just to give you an idea. Now, there is, say, more regulation that is needed, and we will talk a little bit about that when I talk about fairness. And some institutions are trying to cater for that. Me coming from Europe, I like to talk about the GDPR regulation, but also the one that is coming now, the AI Act. Actually, in my city, and Pierre, I have to talk about my city, they just opened a center from the European Union about algorithmic transparency. So that shows basically the interest that the European Union is having on working in that topic. Yeah? So these people over there, what they are trying to do, so we had a meeting in January, and what they are trying to do is basically control a little bit more the algorithms used for big tech companies. And the last bullet point of this slide is to say that this is what distinguishes what I do from that bullet point. These are off-the-shelf tools, which are very useful because you don't need to basically model more, but they are off-the-shelf. So they are not as flexible as we would like sometimes. And this is what I can basically do with my expertise and with the expertise of my students. We can try to build something more flexible for the needs of people. So now, as I said, I'm an operations research person. So I'm giving you there a few references about, the work that we have done, the summaries, the survey that we have done about the work of other people. So the first paper, it was in 2003, and then we were reviewing some of the classification tools. The paper from 2021, we are going to zoom into that paper. It's about trees, which have become extremely popular in our literature for a very good reason. They are built in these off-the-shelf. They are normally built in a, say, heuristic way, and we are developing them in an optimal way, and I will show you why that optimal way is beneficial for the community. Now, as you probably figure out, it's my first time in this conference. I don't do forecasting. This is the only paper in which I did try to do a little bit of forecasting, like everybody else, working with COVID data. But anyway, that's not why I'm presenting this paper. This paper is just to show you that, with optimization, I can basically, choose an ensemble that is good and that it keeps updated dynamically, like we had to do in the COVID times when we were trying to do forecasting. And, this is what we did. We had a good base of basic regressors, and we were optimizing the ensemble. Another example I would like to show you, just to give a little bit of a sense of what we do. Look at this single column of data in a data set with more columns, right? So this single column of data has a structure. So I have here in this conference talking about hierarchical structures. So this is one that it has a hierarchical structure. So what we do in this paper is we try to find a subtree. And why is that we want to find a subtree for this column of data? It's because we want to be more sparse. It's because we want to be less granular, because we have to interpret then fewer coefficients, right? So if I can achieve this with the same accuracy, I would prefer this tree because I have less coefficients to interpret in a linear model. Yeah? So this choice of this subtree is something I can do with my optimization models. Yeah? So the next one is about functional data, and over here what we do is we try to choose, prototypes in the data to explain the clusters in the data through these prototypes. So anyway, this is about the role of mathematical optimization when we talk about transparency. What we are coming now to is these high-stakes decision making. So if we automatize more and more our decision making, we may be putting at risk some individuals, right? So this is what we are trying to solve. Say we are trying to guide the individual with more knowledge about how the algorithm is functioning. So if you went to get granted a loan and you got a rejection, you would like to know why the algorithm rejected you. So this is one of the things that we will look towards the end of the presentation. So what we call counterfactual explanations. So that's one way of improving, say, the interpretability of the model is to give an explanation to the individual. And actually, this is one of the requirements in the GDPR regulation, so the right to an explanation when you are subject to algorithmic decision-making. The second thing, when we are in high-stakes decision-making, is there are plenty of examples in the newspapers about collectives that have been subject to an algorithm and that have been, say, discriminated by that algorithm. So I have the example of A-levels in the UK. When we had the COVID lockdown, the exams couldn't be so those are national exams, say that they are taking into account for the entry to the university. The exams were taken away because they couldn't be done in person, and then an algorithm basically substitute these exams. The grade was substituted by an algorithm, and then some schools were discriminated, and this was all over the news in August 2022 in the UK. So what we want to make sure is that we take care of certain individuals in our data set because there may be only a few of them, or because maybe historically they have been underperforming in the data set. Yeah? So maybe what we also want to do is a kind of a positive discrimination. So we know that, for instance, if you have a data set about income, like we will see later on, we know that a certain gender will have a lower, say, average salary, and that gender we have to make sure that it's not amplifying the bias into the future. Okay? So that's what we are going to try to do today. A little bit of fairness, a little bit of transparency, and a little bit of explanations. Now, the literature is growing in terms of fairness papers, and you can see that, again, within this literature, you also have the contribution of operations research for a very, very simple reason. Normally, we tend to optimize, say, our algorithm for the whole data set, but we may also want to optimize the algorithm for a subset. So you have already two objectives there, and we know how to do that in optimization, right? So you are dealing with a weighted approach or with a constrained approach, and then you can describe the whole Pareto frontier, and that's what we are going to be doing today, right? So this is one very natural way in which we can do fairness. Okay, so you can see there that I was going to give you a little bit of a tour, and if you browse that list of items, then you are going to see trees, you are going to see assembles, you are going to see super vector machines, you are going to see lasso models. So pretty much, you know, I'm just taking you through the main methodologies and show you what we can do in each of them. It's only a sip. And apologies because I have to keep to my 45 minutes, although, you know, Spanish people find those things very, very, very difficult. But I will make sure that I keep to my time. Okay, so I'm just going to start with the first paper. And I'm very, very much in love with this paper. And I'm going to show you why I'm very, very much in love. Because it's actually, I'm going to give you a data set. You are going to be doing classification. And the data set has columns, right? It has features. And what I'm going to be doing for you is actually generating new features. Yeah? You are a little bit patient, but I will show you at the end of the slides that actually what you are creating is a different feature space. And that gives me a lot of flexibility, because I'm just going to build you an ensemble, but with new features, and I'm going to be able to control accuracy and fairness. Yeah? So let me show you what is my starting point. So my starting point is whatever assemble method, tree assemble method that you like, we start from there. Do you like random forest? We will start from there. Do you like XGBoost? We start from there. So that's trained. You gave to me those trees, and now I own those trees, and now I'm in charge of constructing my new tree ensemble. Okay? So it's not the one that you gave me. I'm just going to build a new one. And what is that I will be pursuing in this new tree assemble training? I'm going to be pursuing accuracy and fairness trade-off, because it's always, a trade-off. I'm going to be pursuing sparsity, and I have to be careful to explain what I mean by sparsity. I want to use few features, right? So that's the sparsity for me. And I want to be scalable in the number of observations, but that's because, some of the techniques actually in the literature are not scalable. But I'm not going to bother you much about that scalability. Okay, so I told you that you gave me the trees. These are your trees, right? Now, I want sparsity and I want fairness, so I'm going to be doing something with these trees, right? So I have information about these trees, I know how you are branching, and I know how they are predicting. All that information is available to me. And now I'm going to eliminate some of these trees. Why? Very simple. I want sparsity. So I don't want to be using a lot of features. So if a feature is not chosen, that tree is deleted. Okay. And now that if I deleted some of the trees, and now just going to reweight them, because the weights that you had may not be the optimal ones anymore, because I have deleted some of the trees, so I need to reweight them. Good. So that's the 2 steps. Wrong. I shouldn't say steps, because I do the 2 things in one go. Yeah? But those are the 2 decisions that I need to make. Which trees I'm going to eliminate, and the weights that are the best for my accuracy fairness trade-off. Sorry that I'm bringing you some of these models, but I really need to show you what is behind the machine, right? So this is what is going to be behind the machine. Is this optimization model in which in the first line you are just, doing minimization of the error that you had did. In the second line, you are saying, please use as few as possible features from your data set. The third line is just imposing a regularization. So I want to make sure that I'm not going for one tree, that I have a variety of trees, because you know that with this diversity, you will be doing better. And the rest of the constraints are to make sure that my error is correctly modeled. Yeah? So I don't know whether you realize, but in my first line, the error has 2 terms. It's because I'm taking care of the whole population, but I'm also taking care of the critical group, right? Whatever they are. The women or the people of a certain religion, whatever they are there in the. And you are giving them an extra weight. So basically what you are saying is that you are paying a little bit more attention to the error that you make on these people. Okay? So now, from far away, I guess you don't see anything, but the main message of these 2 plots is in the first one, you see the lines all very, very, very much together. In the second plot, you see a line higher, and the other ones are going down, down, down. Okay, so what is the first plot saying to me? For the whole population, I pretty much have the same accuracy that you have with your own initial trees. So I didn't lose any accuracy. What is the second plot telling me? Okay, your initial trees, sorry for making you look bad, but your initial trees, they have higher error, and I can lower the error, on my critical group. this is my critical group. I can lower the error, giving them more and more weight. Yeah? So this is a very, very easy way of taking care a little bit better of that critical group that your off-the-shelf methodology wouldn't be able to do so simple. Now, one more thing. My methodology is also using fewer features that your methodology will be using, because I guess that you realize that I go flat. Yeah, I go flat. So meaning that I don't need to use all the features in the data set. At a certain point, I cannot improve my accuracy by using more of them. So it's a way of selecting these features. Now, let me go back. And this is why I told you that I like this paper. These little trees, the ones that you have, they are your new features. These are your new features. These are features that model some non-linearity because they are if and then. So what you have done is to re-feature your data set, and these become your new features. And what you are simply constructing is a linear model. Yeah? So just to give you the idea about what we are doing. Okay, so now let me go to another paper. I'm going to spend a little bit more time here because this is a whole thesis. So one of our students a few years ago started to work on optimal trees. Now, in our community, the number of papers on optimal trees is increasing exponentially. So we have discovered that we can do something. And these papers are growing. So there are teams in the MIT working on optimal trees. There are teams in Cornell working on optimal trees, etc., etc., etc. Our trees are slightly different, and this is what I would like to talk about. So why do we like trees? Trees, to start with, they are what we consider white box. So actually, if I can have a good accuracy with a tree, then I will be extremely happy because that's considered a very transparent thing. Moreover, if I want to have fairness, and if I have an optimization model behind it, it's very simple. I put a constraint or I put a new objective, and then I will be able to get the trade-off. Yeah? So it's very clear why we are interested in trees. So all these papers that I was talking about, they are surveyed in this paper that I'm showing there. Now, our trees, the difference with the existing ones in the literature is that we are going to avoid going left or right. Every individual will go left and right. Left with a probability p, right with a probability 1 minus p. Yeah? So that's what we are doing, probabilistic trees. Now, this p, I'm going to show to you how we model that one. And the usual thing, we want the accuracy, sparsity trade-off, we want fairness, etc., etc. But remember, this is what you have to remember about these trees. We are going to have a very beautiful local explainability. And in a second, I will show to you. Yeah? So that's the only thing that you want to remember about this paper. Local explainability that the regular trees that you have, say, from the off-the-shelf cannot give you. Okay, so, yeah. Sorry, but I couldn't stop. She's very happy. She just got a prize from the Classification Society, and this picture is from a couple of weeks ago. So my trees are probabilistic. So you can see that at the top of my slide, I have a tree in which I have a probability to go left and a probability to go right, and that will depend on yourself, right? So you have features. I input that features in a cumulative density function, then I get a number, and then that's my probability of going left, and then 1 minus that 1 is my probability of going right. Yeah? So I'm applying that cumulative density function of a univariate random variable, And the most natural one, it would be the logistic function, right? Because in the logistic function, I could go, for the orange option. That's what trees are doing currently. I go left or right with probability 0 or 1. And what we do is the green one, which is the smooth way of making decisions. And it's very simple why I want to do that. Because why do we take hard decisions, yes or not, if our data may not be so good data? So it's much better to take a soft decision than to take a hard one. Now, my prediction function, and this is for regression, but we also have trees for classification. So for regression, what I'm doing is I have a probability of ending at each of the leaf nodes. I have a regression model at each of the leaf nodes, and I can combine them, right? That's what it's saying. I put there a linear regression model, but I could have put any other model that you like, yeah? So that's the way I'm going to predict, and to build that model, I need to solve a highly nonlinear optimization model, yeah? This is not for free, it's highly nonlinear because these probabilities are the product of probabilities, so it's a highly nonlinear model. I control sparsity, the local sparsity, so at each of the branch nodes, I will control how many of the features I'm using, but I also control how many of the features I'm using globally in my tree, and this is the global sparsity. So I told you that this is the thing that you need to remember from this paper. This is local explainability. What does it mean? Well, we made a prediction for each of you. So we made a prediction for each of you. And for each of you, I can show how sensitive you are when I move your features. So what we are having over here is feature criminality. So this is house prices. So if I have a higher criminality, then my house price should go down, right? And that's what you see there. But that sensitivity depends on the house. And you can see the span of this sensitivity. So why can I get this plot directly from my optimization model? I'm using partial derivatives because I'm modeling my tree in a continuous manner, so therefore I can do partial derivatives. The trees that you get out of the shelf, which are yes or not, they cannot do that because you have discontinuities that you cannot handle. Okay. Now, so these trees are being used for tabular data, numerical, categorical, but we also wrote a paper to use the trees for functional data, so multivariate functional data. So here you have a data set, and you have many curves, and then you take the first derivative, you have many curves, and then you take the second derivative, you have many curves, and then what we are trying to work is with this data. And how do we work with this data? Well, we are going to have, again, cuts, yeah, oblique cuts, but now I have to be a little bit careful because to have an oblique cut with functional data, I also have coefficients that are functions. Now, because I always thinking about explainability, I would like to pursue, again, in this paper, explainability by doing what? By detecting key intervals in your functional data. So I don't want to be looking at my whole curve. Maybe there are only certain parts of the curve that are important for my classification or regression task. And how do I detect that? Well, I'm going to assume that the coefficient of a functional feature is going to be piecewise constant. So in a zero area, it means that this interval is not playing a role, and here it means that the interval is playing a role. So what do I need to decide? I need to decide the intervals, and I need to decide the coefficient in each of the intervals. So that's what I'm showing to you here. I need to decide these two things, and then what I can impose is sparsity in two ways. I can impose a sparsity in the sense that I would like my intervals to be narrow, and I would like also that my intervals on the overall are not using a lot of the curve. So this is an example of the output of our methodology, but if you like, this is what you will be having if you are putting more emphasis on the sparsity. So if you are putting more emphasis on the sparsity, your intervals are going to be very narrow, but probably you don't do that well in accuracy. So it's again, we show in this paper the trade-off between accuracy and sparsity. Good. So now I'm going to show you, this is going to be just a tiny, tiny, tiny idea, you know, that we just did with one of our master students, but it's actually beautiful because we all know that support vector machines are based on kernels, right? So I kernelize my data and I have a better accuracy. What if I want to have a fairness SVM? I just need to make my kernel more fair. And I'm going to show you that. I have left out the math, but I will show you in a second. So what are we doing in a super vector machine? We are finding a separating hyperplane. If you are doing this with kernels, then you are in a different space, but still you are separating with a hyperplane in that space. This is the classic quadratic programming model that you need to solve, and from there you get your scores. So what are my scores? They are a linear combination of kernel computations. And if that score is above 0, then you go to the positive class. And if the score is below 0, then you go to the negative class. Good. OK. So just for the sake of time, I go here quick. I told you that I want to be fair. Yeah, that's what I'm doing here. So what I'm going to be doing to be fair is I'm going to penalize the unfairness again in the objective function. But have a look. What is unfairness in this paper? Well, you have scores, right? And I told you that if the score is positive, you go to the positive class. If the score is negative, you go to the negative class. So think about the positive class being something good for you, being granted your loan. Yeah? So what you would like is that if you are in that possible to discriminate group, you wouldn't like to have your scores, say, very different than from the rest of the population, because if they are much lower scores, then you are not going to be granted the loan. Yeah? So what you want to do is that the distribution of the scores in the sensitive group and in the non-sensitive group, they are not showing a lot of mismatch, because then you will have discrimination. So what am I doing? I'm trying to bring these two distributions closer by. And I think for this community, this is very common to do. And I'm doing this with the Wasserstein distance. So I'm basically taking care of the Wasserstein distance. And there is a very, very simple reason to take the Wasserstein distance, because this is another optimization problem, and then we can put the two optimization problems together. It's another optimization problem that, is a transportation problem. Yeah. And we can put them together. So now, this is what I was telling you. It's a very tiny idea, but it's very beautiful. We do the math, and then look at what is happening. The Wasserstein distance, it just needs to basically link scores from one distribution to another distribution, and it's done with a pi vector. Yeah? So it's the optimal transport, the pi. Well, imagine that I knew was the optimal pi. So if you knew the optimal pi, I can do the calculations, and I end up having, again, a super vector machine with a different kernel. A kernel that is supposed to be more fair, because what it's doing is the original kernel plus a term in which you are looking at the differences between the sensitive group and the non-sensitive group, and therefore you are modeling there the fairness. So if I have to be honest to you, I don't know the optimal pi, but that's not a problem because what I do is an alternating optimization procedure in which I solve for the pi and I solve for the supervector machine, and this is what I end up having. The typical message that I gave you at the beginning of the presentation saying, you know, if you want to look at your accuracy, you know, the accuracy is pretty much flat over here, but look at what is happening with your versus time distance. It's decreasing immediately. So what is happening is at the beginning you had a mismatch between the two distributions, but you can put, they are much closer by, but just penalizing a little bit your unfairness, just a tiny bit. Yeah? So meaning you don't lose accuracy, but you are not discriminating this other group so badly. Now, we also did the same with the fair lasso, but for the sake of time, I'm just going to show you one slide. So here we are not doing versus time, although there is a kind of a versus time behind the scenes. But anyway, what are we doing here? This is lasso for regression. This is a data set in which we have GPAs, yeah, to enter to the university. And then you can see again a mismatch between these two populations, meaning that the one with this shift more towards the, well, it depends on the right or your left, but anyway, in that direction, that one will have a higher chance to enter to the university than the other one. And we don't want that. We don't want that discrimination. So we have to get them closer. So we count, yeah? So we put a threshold, and then we count how many people are on the tail, and then we would like that these two numbers in proportion are very similar for the two distributions. Now we are having 0, 1 decision variables to make, but it's a mixed integer quadratic problem that we can give it to commercial solvers without a problem, and then you can get it much closer again without losing much accuracy. Yeah? So, okay. So now I need you to shift gears for the last bullet point. Now you have constructed your machine learning model. It's ready. But you have to explain the decision made to an individual, right? So this is what I told you, that it's these contrafactual explanations. Yeah? So have we heard about contrafactual explanations? Yeah? Yeah? So what we are going to say is to shed sunlight to the individual on what it needs to be changed, what that person needs to be changing, to change the decision. And our contribution is going to be that group word that you have there, but I will make that very clear. Okay, so I told you that my model is built. So I have a model that is probabilistic, and the decisions are going to be made with this probability. So if that probability, think about a logistic regression. If the probability of being in the positive class is about 0.5, you will give that person the prediction of positive, and if not, you will give the prediction of negative. So a contrafactual explanation is another individual, it's another observation. It can be actually made up, or it can be another observation of the data set, but it's another observation. Such that, yeah, so I got rejected the loan, I went to the bank, I got rejected the loan, so what I'm searching is for another observation that is not very far from me. And that new observation is going to be granted the loan. So that new observation should have a higher probability of positive than me, so that I'm learning how to move towards this new observation, and therefore I have some guidance of what to change. So is the problem clear? So you can see that it's naturally an optimization problem, and I will show to you in a second. Yeah? I have some graph here to show what is going on. And you can see that there are some original features, and the contrafactual is just basically new features. And what you would like is that these features basically are not very far away from each other. And the narrative that you will give is, you know, you have been rejected, but if you change your salary and if you change the number of accounts, then you would have got the loan. So let me show you. Again, it's rather, I would say, new topic. Actually, there is a little bit of disagreement, as usual, who came first with these contrafactual explanations. Yeah. So I was facing that in a PhD defense a few months ago. But anyway, what type of information do we have? We have a feasible region. And it's very clear why I need a feasible region for this instance, because I cannot change my gender. So if somebody would like to give me some information about how to get my loan, that has to be not moved. So that's a constraint, for instance. But I could also say I don't want to move too much my salary, because that would be difficult to believe that I can match my salary and so on. So there are constraints, and there is also a cost of moving. So you can use L2, you can use L1, or you could even use an L0, because maybe you don't want to move too many features. Yeah? So sparsity. And the optimization problem that you need to solve is by objective, because you wouldn't like to have a lot of effort to move to that new observation, but you also would like to have an idea of how to make your probability as high as possible. So I put a negative sign because I'm minimizing, but anyway, yeah? So these are the two objectives with my feasible region. So that's in the literature. So I'm just doing a couple of steps because I can actually show to you that this is normally what they solve in the literature. They work with score-based models. Many of the models that I was mentioning today, they are scores-based. So logistic regression, SVM, neural network, random forest, XGBoost, they are score-based. And then what you are trying to do is you are trying to get a high enough score. So in the supervector machine, it will be a score above 0, because then you will be predicted positive. Okay, so that's in the literature. Now, what we do is we are not only trying to help the individual, but we are also trying to help the modeler. So how many times you think, okay, I would like to know what are the relevant features in my model, right? So we do this all the time. We build a lasso model because we like to use as few as possible features, right? Same here. You would like to detect as few as possible features so that if you manipulate them, if you change them, you can increase the probability of getting granted the loan. Yeah? So this is one of the reasons why I need to go through a group approach. So I don't want to be solving contrafactual problems for each of you individual, but I would like to solve all of them in one go with one single model. Be careful, because the model is quite big. It has to decide my contrafactual, it has to decide his contrafactual, and so on, and so on, and so on. So all these decisions are made with one single model. The beautiful thing is that I'm going to be able to control how many features I'm using. So these are some of the reasons. So basically detecting critical features. And this is the output that you get if you do so. Now, from far away, you probably cannot see much, but I guess that you see that there is a column here that looks green. And there is another color here that looks pink. And then what is saying to you that in this data set, which was again the housing data set, you would only need to move 2 features to basically be predicted to be positive, meaning to be predicted that it's a good house for a high price, that it can be sold for a high price. So what we are doing here is, if I allow to move 2 features, then I will need to change basically the LStat variable, and I will need to change the number of room variables. So in this way, you are showing in an alternative way to the modeler which are the relevant features that allow you to increase your probability of being positive. Now, if you would like to use more features, then you have a whole Pareto front, again, in which you will have to use, you will have, say, closer contrafactuals at the cost of having to change more things. Now, the final plot that I would like to show you, and then I keep it almost to my word to finish in 45 minutes, is another way of the modeling learning, say, from the data set, is to say, instead of finding contrafactual for every individual, and the contrafactuals are tailored to me, what I can do is I could detect 3 contrafactuals for the whole data set. And we will be clustered towards one of these contrafactuals. So we will be assigned towards one of these contrafactuals. So we did this in another paper, and then what you have over here is the contrafactual is here at the bottom, and at the bottom, and the observations that will be assigned to this contrafactual are these ones, and you can see that this cluster is much larger and this cluster is much smaller. And then obviously you can see that in this cluster there are common features because these features are all very similar. Yeah? So in some sense you are clustering, but keeping in mind your prediction task. So you are not clustering your features, you are clustering your features with information about your predicting task, which is encapsulated in your P information that I showed to you in your in the optimization model. Okay? So I think I will leave it here. I hope that I have shown to you the flexibility that I have with my optimization models to basically explain different type of data. And just to say that most of the presentation was about classification and regression, but we are also doing some work where the decision-making problem is more complex. So we are working with the benchmarking of utility companies. That benchmarking creates already a linear program that I have to solve. And when I try to find the contrafactuals, I end up having a bilinear program that I have to solve. But then I can give feedback, which is of much more quality than the literature has done up to now. So thank you very much for your patience, and glad to see you.
Thank you, Professor, for this very inspiring presentation. It's amazing to feel we live in a world where there is a fair kernels. We can now open to the Q&A, so if you have questions.
So for every leaf, I will need to have one of these cumulative density functions. Yeah. So I have to decide the parameters. So at the end of the day, what I have is it's a linear expression, but then I put that linear expression into your cumulative density function. So if you think about the logistic function, I will have 1 divided by 1 plus e to the negative of a linear expression. And I have to do that for every single branch node. Yeah? So I have to do this for every branch node. Then in the leaf nodes, I could do whatever I want. I could basically predict with the mean, but we don't do that because we can easily put there a linear model, and then we can adjust much better to the data.
Thanks. My second question was, I saw you using the housing data set, Boston housing data set a lot. Yes, some have expressed some ethical concerns about this data set. Is that something you consider, or is that explicitly part of the research?
For the slides, it's much easier to present that data set. But of course, I mean, we always, in our research, we always test in many data sets. Yeah, so I agree with you that it's not good to present only one data set, but for the sake of the presentation, it's easier for me. Yeah. But we have done this with many data sets, that people use in the literature.
Yeah, okay. My point was not about using just one data set. My point was more about there's been some concern about it explicitly encodes feature B, which is the proportion of black people in the neighborhood, and that is said to be, well, completely incorrect and based on some 1970s assumption about racial segregation in the neighborhood.
Exactly. And then I didn't present it today, but in one of the papers, basically we try to control the fairness looking at that group. So thank you very much for raising that. But yes, it has sensitive information, and in one of the papers what we try to do is to avoid discriminating the people from that sensitive information. So actually we did this with the optimal trees, and we have also done this with the tree ensembles. Yeah.
Okay, thank you.
Thank you.
Thank you. It was very interesting, your presentation, and I think my question is related to, we usually use the off-the-shelf tools that you mentioned, because I think in some cases, and I would like to know your opinion about it, the optimization problems, the Taylor optimization problems might be super complex, non-convex. So how do you guarantee a solution and optimality?
I love that you asked this question. I basically took away some of this information, but I did try to say, you know, when I was building the optimal trees, I did try to say that it was highly nonlinear, just to be sure that I'm not overclaiming to the audience. However, some of the other models, and I think I mentioned very briefly, some of the other models will really take care of the scalability. So for instance, when I was talking about the tree ensembles, you see that I have a linear model with some 0-1 variables, but actually the 0-1 variables are only for the feature selection. I have no 0-1 variable for the observations. So if you think about a MIP, this is pretty much easy to solve. Yeah, that's very cheap. But I do agree with you that not everything is scalable. Actually, some of the optimal trees, this is what we wrote, we started to work in this area. Most of the optimal trees that you find in the literature, they use MIP formulations where you have 0-1 variables for every single individual. That doesn't scale. That doesn't scale. Yeah, so I agree with you that and that's what the community is doing. The community is working very hard to give more scalability in machine learning. So some years ago, you will find machine learning problems being handled by optimization colleagues solving n equal to 50. That, yeah, we are working hard on trying to avoid that limitation. Yeah. So yeah, I hope I answered the question.
I was wondering about the group counterfactual work that you did. So is there any notion of causality in this?
Yeah.
So I was a bit surprised not to see.
Yeah,
you know,
that's also a good point. So we are starting now to work on causation with another student. This is where the whole machine learning community is going to. Yeah. So maybe if we talk to each other in 2 years from now, yeah, somewhere, sometime, yeah, we will give you some more on that.
Thanks for the presentation. You put a lot of emphasis on transparency and explainability. And in the explainable AI literature, a discussion that's currently ongoing is that the metrics, or at least the way we academics speak about it, actually doesn't connect to reality. That most of these metrics are not actually tested with practitioners, that actually they make the models explainable or transparent. So I would like a comment from your point of view, well, regarding the literature, but also your different approaches, because you avoid the off-the-shelf explainability tools.
Yeah, the off-the-shelf explainability tools, as I said, fine when you don't want to get the hands dirty with something more, say, yeah, like we do. But there are problems with correlations in those off-the-shelf tools. They try to solve those in other papers. They will work with certain type of data. They wouldn't work with more complex data. That's what we try to do. And by the way, they are a second step to what you did before, meaning that there is a drop in accuracy in which you don't have to control, because there is an approximation that they do, and that approximation cannot control the loss in accuracy in the new surrogate model that you have built. That's what I try in my good or bad way. That's what I try to avoid. I try to say to have control. Yeah, my first bullet point. I try to have control of the two things in my model. Yeah, but maybe more costly, like your colleague said. But then I can basically ensure that I don't have a big loss. And you saw me showing some plots in which I will have basically a flat line because I don't lose any accuracy with just imposing a little bit of explainability or fairness. But I mean, it's not like I'm putting into the garbage bin, you know, these tools, because they are shedding some light. But they also have some drawbacks, like I'm sure that you have read in the literature.
Any more questions? Great, so I think we can finish sharp on time, and thank you very much again for this great talk.
Thank you.
It was highly technical, but so engaging.
You want to follow?
Okay.